so at least in one of my classes we didn't get to this, and that is how non-conservative forces will affect the conservation of mechanical energy. The whole point of conserving mechanical energy, conserving anything, is that the quantity doesn't change. So your mechanical energy at the start has to equal the mechanical energy at the end when it's conserved. When no non-conservative forces act. In other words, nobody pushes on it, there's no applied forces, there's no friction, there's no air resistance, things like that. And that means that this would be straight up. Well, if non-conservative forces act, if friction acts, or somebody pushes on this thing, what will happen is this will not be true. Well, by its definition, that means the mechanical energy initially will not equal the mechanical energy final. Okay. Which means that when we compare the final and the initial states for mechanical energy, there will have to be a change in the mechanical energy. In other words, we could find that change by doing the final mechanical energy minus the initial. There will be some sort of change in the amount of mechanical energy that it has. So, by the way, if you hear chatter in the background, it's people coming in to eat their lunch here. Okay, so what's going to account for that change? Where did the energy go? So, if I push, no, let's not push. Let's just go with a simple example. Let's say a box is sliding with an initial velocity. So let's say it has an initial velocity of 5 meters per second, and it's 2 kilograms worth of box. And we're going to go along a level floor. So we're going to not even worry about potential energy. So what is its initial initial mechanical energy? Since we're going to put it on the ground, where we're going to call H equals 0, none of it is in the form of potential energy. All of it is in the form of kinetic energy, which we know. 1/2 mv squared. Let's take care of that right now. It's going to be half m, so that's going to be 1 times v squared. It's going to be 25 joules. Keeping the numbers simple. So the beginning mechanical energy is 25 joules. But we're going to allow friction, a non-conservative force, to act on the box to the point where we'll let it do what it will, if friction's present, what it will almost certainly do eventually, and that is it'll come to a rest so that its final speed is 0. What's its mechanical energy at the end? Well, remember, I can't say they're the same. Certainly they're not, because the darn thing stopped and it didn't go up or down, so it can't have, and that's because this non-conservative force acts. The final mechanical energy, once again, there's no potential, because it didn't go up or down, is all in the form of the final kinetic energy, which, if it stopped, would be 0. So in this simplified example, we started out with 25 joules of mechanical energy, and we ended with 0 joules. So where did the energy go? Well, there's only one place it could have gone, and that was friction. And what we say is that friction, I think you would agree with me on this one. Whoops, I don't know how that happened. Try that again. Friction, there we go. Friction didn't work on the box, right? In fact, it applied a force over a distance. I don't know what that distance is. I don't care at this point. But it certainly did apply its force over this distance. Now, the force of friction would have been this way. But would have been this way. There you go. You can't be taught. Well, the displacement would have been this way for friction. So it would have done negative work, wouldn't it? This is our way out of this. What was our change in mechanical energy for this situation? It would be the final, which is 0, minus the initial, which was 25. That means our change in mechanical energy is we lost, negative, 25 joules. How much work do you think friction did? Even if we don't know the distance or the force, how much work do you think friction did? I'll give you one guess. See, the work done by any non-conservative forces is going to show up as that change. Because if conservative forces do things, it doesn't change the mechanical energy. But non-conservative forces are the very thing that produce this change. This will end up with us giving this final idea. And that is the change in mechanical energy is always going to be a result of the work done by non-conservative forces. Now, could be more than one of these, so we might need to do different works, some positive, some negative. Maybe we bring up the net non-conservative force, so maybe friction's working one way and somebody's pushing another, and we just find the net non-conservative force and go from there. There's a lot of different ways to look at it. And in fact, there's a lot of different ways to look at this equation. You could, if you happen to read the textbook on it or something, or look on it, there's a few different ways to look at this. That means one way is our mechanical energy final minus our mechanical energy initial equals the work done by non-conservative forces. Oh, and by the way, another phrase you'll see for that is the work done by, they call external forces. That works as well. You'll also see that phrase. So don't be, these two are equivalent. Work done by external forces, ones that aren't gravity or conservative. You'll also see that phrase. Now, I think probably the most common way we look at this is this. We say your final mechanical energy has to be equal to whatever you started with. Now, I'm going to say plus your work done by non-conservative forces. But keep in mind, does it have to always be plus? In our example, it's actually a minus because the work done was negative. So sometimes this will be positive, sometimes it'll be negative. Positive would be an example of, let's do it this way. Let's say we have no friction involved. So we'll say something's on wheels. A wagon, a small child in it. It's not my kid though, I swear. So let's say I apply a force. I push horizontally on this. Force by Wellborn. I'll call force applied because you'll see that more often. That is an external or non-conservative force. So if it started at rest, its final velocity will be something more. It'll be flying, right? So there would be an increase in mechanical energy. The final energy would be larger than the initial. Well, I did positive work, didn't I? I pushed this way and it was displaced that way. So in that case, you would add in the work done by the non-conservative force. So non-conservative forces do not have to detract from the mechanical energy. They can, like in this case, add to the mechanical energy. And if you have multiple, maybe I'm pushing the thing and there's friction. Maybe the wheels fall off and I can still have an increase in mechanical energy. I might not get as much if there's friction because the work done by me would be positive and the work done by, then you have to take away the work done by friction, which would be negative. So it can get more complicated than that. And if I push uphill, that's interesting too, because then I might not increase speed at all, but I did increase potential energy, which means I would still have more final mechanical energy. So there's a lot of ways to complicate matters. And be rest assured that we will complicate matters. But this general idea, however you want to look at it, is when you have a force that involves friction or somebody pushing or a rocket strapped to something, I swear I think there's one problem like that. So those are all examples of non-conservative forces. Notice, to know the work done, I don't need to know force and distance, necessarily. All I need to know is the change in mechanical energy. I could then, if I knew the force, find the distance, or vice versa. If I knew the distance, I might be able to find the force. So keep that in mind.